we need to make sense of that. It's an extremely important social signal. And we, as a matter of fact, we treat, process and use emotions in many different applications. One of the very hot topic right now is sentiment analysis. So people take like a range of tweets and try to figure out if those tweets are like evoking, eliciting, like are kind of are mirroring a general mood of happiness, sadness, fear, anxiety, things like that. And actually the stock market are even plugged on those kind of automatic sentiment analysis to see, oh, the mood is pretty bad, let's sell, or on the contrary, everyone seems to be happy, that's probably a good time to, I don't know, buy or things like that. So the importance of emotion to machine goes way beyond just our robots interacting with humans, and that's also the reason why there's a lot of research on those things. Now the question is, okay, fair enough, it's important to recognize emotions. Is it important to express emotions? Well, I don't know if you've heard about the medial equations before. Maybe Serge mentioned it 2 weeks ago, I mean at the beginning of the lecture. I encourage you to check the Wikipedia page. It's a fascinating work. But basically what it says is us as humans interacting with technology, computers, our phones, our cars, our robots, as a matter of fact, cannot help but trying to attribute emotions or an internal state that would represent something. So if you start yelling at your computer, even though you know that it's just like you're pretending that you're yelling at your computer, you're still doing it. And after 5 hours of trying to install Linux on your computer, you might really become like a bit angry at the computer, even though it's emotion. So in that sense, because it's there, it's important for robots or machines to be able to manage that. And one way of managing that expectation is to be able to generate and actually like match or manage the expectations in terms of emotions. So that's pretty much what we said, what I was saying. Like, because machines knows that the humans are going to ascribe emotions to the machines, it's quite important that the machines are able to manage and handle that. So a bit of, So how to represent emotions? Let's go straight to the point. We've seen those 6 emotions. So the first basic approach would say, okay, I have a picture of a face, one of those 6 faces, for instance, and I want to say, yes, this face is or is not, does include or not anger, disgust, fear, happiness, sadness, surprise. You can add your own if you want to. So it's really like the on-off. Is there or not some happiness or not in this image? So why is it a poor approach? I think I already mentioned that before. Well, essentially because as a matter of fact, we are never completely happy, never completely sad. Reality is more complex than that, and it's more continuum. We are somewhere in between. So then we say, okay, fine. We can just represent each of those 6, 7, 8, 9 emotions as a value between 0 and 1. We still have a slight problem with that. Can you figure out what would that be? Well, pardon?
It doesn't tell you, if it does represent emotion 0 and 1, it doesn't tell you exactly what emotion is. Everything is.
So yes, but that's something we have to deal with, right? The fact that at a given point in time, one person might be in emotional state at the same time that overlap, and when we read a face, we try to recognize emotions in a face. It might be the case that there's a bit of many things in that face, but you're right in the sense of there is something that are contradictory. We cannot have at the same time full happiness and full sadness, and a model like that would make it possible. Our system could come up with situations where we are completely both sad and happy. So that's probably not the best way of representing emotions in a system. So we want continuous representation of emotion in space in such a way that we cannot have those kind of contradictory situations. There's several, like many people work on that. The most famous way of doing this model is what we call the circumplex model. It's a rather old model. It has been introduced by James Russell in the 80s. And it basically maps all the emotions to a 2D space. The arousal in one direction, from a very strong emotion to a very weak or light emotion, and the balance on the other axis, something very pleasant to something very unpleasant. And we can place many emotions on that circle. So happy, for instance, would be something very pleasant. Might be like you're not super excited, but you're very pleased. Something very pleasant and very intense could be like elation. You're being enthusiastic about something. On the other side of the arousal axis, something very subdued is like being bored, being very calm. So something very calm but very negative would be like being depressed, sad. We see here like upset, stressed, nervous, tense. We can place many emotional states on those two axes, and it's nice in the sense of it's only two values. Like it's a simple model. So if we play a little bit that game, so this is a range of faces. Well, it's a bit small to recognize, but we can see here a face that is almost asleep. That's basically like a neutral. The valence is neutral. There's nothing positive or negative about that. It's just completely inhibited. There's nothing happening there. And there, on the contrary, you have someone that is very happy, very enthusiastic. Someone who is not, this person, for instance, is not in too much of a negative state. So it's more like what was called tense here. It's slightly negative, but it's not very negative, but it's still something very strong, a strong emotion. Here you would find the people that are very, very angry. This little girl there is maybe like very sad, crying, so it's a strong balance, but not a very strong arousal. So she's not like, she's not asleep, she's not super excited, she's just sad. So we can place many faces there. And as you can see, like for each of them, we can associate just two coordinates, V and A, balance and arousal, and place the faces there. Right in the middle, at 0, 0, you have the most neutral face. There's no specific emotion right now on that face. Yes? A slightly more complicated model. We had one more dimension, is the PAD model. It was introduced actually even before, it was also introduced by Russell, but even before the circumplex model. So it first started with a slightly more complicated model and then went down to only two axes. So in that case, PAD stands for pleasure, arousal, and dominance. Pleasure would be how pleasant is an emotion, anger and fear are unpleasant emotions, score low, joy is a pleasant, so it's quite close to the balance axis we had before. Arousal is the same thing, the intensity of the emotion. So yeah, the difference between anger and rage would be that the anger is less intense than the rage, for instance. Boredom would be on the contrary, like unpleasant and very low intensity. And dominance is how do you control, or how the emotion controls you. So the difference between anger and fear is that anger is a dominant emotion, that's you being angry at something. Fear is more something where you're passive, something you receive, you're scared of something. So you end up with 3 dimensions. This list here of many, like something like 25, 30 emotions, and the mapping to this PAD model comes from this paper. There are other mappings as well, but that's a good starting point if you want to try to map like labels, put labels on emotions. So if we take, for instance, joy has very high pleasure, 0.82, so that would be somewhere there. The arousal is average, so we would be like somewhere there. And dominance is rather high as well. So it's something that you generate, you're joyful about something, it's quite positive, quite intense. Shame, for instance, shame is an interesting one. So the arousal is almost zero, so it's on that plane, on the plane dominance to pleasure. And shame is very negative, the pleasure is quite negative, and the dominance is quite negative as well. It's something that you receive, you're passive in the sense of that emotion. Okay, so those are, so we've seen like two models that are continuous models of emotion, the circumplex model and the PAD model. We've seen as well simpler model where we just put labels, like names really, that are all derivative of this Ekman model of those 6 basic emotions. So how to map automatically a face onto one of those models. Before jumping onto that, we need to talk a little bit more about action units. Have you heard about action units before? It's action units are a part of a bigger thing called the facial action coding system, FACS. And the purpose of FACS, that was again developed by the same guy actually, Ekman, was very active in the 70s, 80s. His purpose was to try to figure out a formal way of describing our face. What is the current state of our face? What are all the small parts of our face that actually convey some significance to interpret emotion, but other things as well. It could be like, for instance, when you're talking, to extract some, maybe not lip reading, but at least some features of your mouth, things like that. So there is a whole taxonomy of human facial movement. In total, there's something like 70 action units. So small parts, small facial movement or facial posture that are encoded in the system. Let's have a look at some of them. So those are the action unit 1, action unit 2, 4, 5, 6. The numbering is standardized. So action unit 1, always refer to that one. And the first one, inner brow raiser. Okay, we have that describe the fact that our eyebrows in some cases might be higher, if you want, than the outer brow, the outer side of the eyebrows. This is the muscle that is actually, or the muscles that are actually linked to each of those action units, because the action units are tightly connected to actually the muscular distribution of your face. So okay, that's one. An obvious one is the eyebrows lower. Okay, action unit 4. Before like that, then the action unit is present on our face. Upper lid raiser, cheek raiser. So that's, we can already see that. Okay, if this action unit is present, so my cheeks are going up, that might be a good indicator for happiness, for instance. Because when I'm very happy, like that, my mouth will have a specific shape, of course, but my cheeks might actually go up as well. There's many others. Nose wrinkle, that might be being angry, for instance. The way we move our lips. So lip corner puller, the names of the action units is really funny. Is that the lips corner are going away from each other. Cheek puffer, dimple, lip corner depressor. That would be definitely useful for sadness, to encode sadness. There's many of them. So I put, yeah, I like the jaw drop. That. Eye closed, lip suck. And there's also action units that describe more actions. Not something you can just extract from one picture. You need to see a sequence of images of the face to be able to recognize them. So blink, wink, and other action units that describe the features of the whole head. So like turn left, turn right, tilt, up, down, things like that. Head up, head down. So we have all those degrees of freedom. I told you in total there is more than 70. I only did show like 40 of them. So if we were able to extract from a picture, automatically extract from a picture, from a face image, all those action units, we would have a very nice 70 degrees of very, very nice vector features with like 70 degrees of freedom. That would be just perfect for classification. Do we have that available? Yes and no. So there is no tool that would do that automatically, but OpenFace, which is an open source library, can extract, is like, as a network trying to extract 17 of those action units. So some of them. It's not the first 17 ones, it's 17 action units. Let's give it a go. Let's see if it works. I'm going to compile it this morning. You can just clone it and compile it. It's actually quite simple. It works on Windows as well. Feature extraction. I'll tell the software to my webcam, device 0, and then visualize action units. Let's see. But it's using my webcam, right? Now, if I'm looking, well, it's going to be difficult for me to look at the screen and the webcam at the same time. But let's look at the webcam. If I smile, for instance, you should see some of the action units skyrocketing. Now, if I look like I'm surprised, so jaw drop is the action unit 26, the last one. If I do that, yeah, it becomes very high as well. If I look sad, maybe. So it seems to be useful information if we want to recognize emotions. Let's see if we can do something with that. I'm going to stop it. So OpenFace can only recognize 17 action units. Those those 17 ones. So jaw drop, lip spark, dimpler, lip tightener, lip stretcher, chin raiser. When you don't know, extra. So equipped with that, let's see if we can build our own emotional classifier from scratch. What do we need if we want to do that?
Camera.
Hmm?
A camera.
Yes, but to build the classifier itself, to use the classifier, yes, you probably want a camera to take pictures. Examples. What would be the data set? The data set. And what do we need as a data set exactly?
Pictures of different emotions.
So faces, labeled faces, and the label being the emotions. What else do we need? So we probably need to pre-process those faces, because if we take just random pictures, the faces will be all over the place. So we really want to pre-process them. Then using something like what I've just demonstrated, extract features like the action units. Maybe other things. Can you think of other ways? Like been showing action units, but there's other ways to recognize. Oh, I mean, there's other ways we've already discussed before over the last few weeks to recognize things on faces.
Classifier?
So we are going to try to build a classifier, yes, but what exactly? Do you remember how we did work out face recognition?
Cascade.
So yeah, but the hard cascade was just an optimization at the end to make it faster. But the key idea was to take faces, like classes of people that you want to recognize, so maybe like 10 people that you want to recognize. For each of, you take all those pictures, you compute a PCA, you compute the PCA of all all those pictures and you project those high-dimensional pictures into a few features. Then in the last part is when someone new appears, you take that new face, you project it as well, and you try to find the nearest neighbor in your PCA space, because it's a much smaller space that contains the important information. That's how we did for face recognition. But we can see the emotional recognition as the exact same thing. Basically, we have 6 classes, for instance, fear, happiness, anger, things like that. And we have a new face arriving, and we want to see what is the closest of those 5 categories. So I do the same thing. I take a big data set of many different emotions. I project them into a PCA base, and when I see a new face, I try to match it to the closest one. Of course, when we were doing face recognition, what we were trying to figure out is, okay, between you two, what are the facial features that are quite different? Okay, maybe you don't have the same hairs, maybe you don't have the same ears exactly, and so the PCA would learn to distinguish between all those faces. Now, instead of distinguishing between faces, we want to distinguish between emotions. So if it's a smile that comes from a woman, a baby, old lady, that should not matter. The only thing that matters is the fact that the mouth is going up. So it means that the way we are going to prepare our dataset and learn it and try to reduce the dimensionality of those images must take into account the fact that those are the features we are interested in. And maybe you remember, I mentioned last week one algorithm that was really good at, because the PCA take a lot of images and try to find the features that are the most, that distinguish the best all the pictures in our dataset. But in that case, we don't want exactly to do that. We want to have many examples of happy people, many examples of angry people, many examples of sad people. And we don't want to distinguish within those classes. We want to distinguish between the classes. You remember the algorithm that does that? The LDA, linear discriminant analysis. It's a bit like PCA. It tries to find a new base that reduces the dimensionality of your image. But the way the base is selected makes, try to increase the difference between each of the classes, which is exactly what we're trying to do. So that's something we could try to do. We will play with that. So we need a data set, we said. We need some pre-processing of faces to normalize them so we can easily compare them. We want features to extract, so depending on what we're going to, the algorithms we're going to try, we'll see what works best. And then once we have our features, we can classify them into emotions. What is the easiest way of building a dataset? Ask Google. So yesterday morning, I spent 1 hour typing human face happiness, human face anger, human face sadness, and I mean those 6 emotions. And I just, with Firefox, you right-click. Actually, let's do it. Oh, okay. My internet connection does not seem to work very well, but that's fine. You just do that. You right-click. You do page info. You have the list of all the images on the page, and if you scroll down a little bit, like Google will dynamically load more images, more images, more images. So in one go, you can save. I think the maximum amount of images that Google will display on one page is 380. So you right click and you store on your computer in exactly 10 seconds 380 faces, happy faces. So of course then there's a bit of manual cleaning to do. So like for instance this little girl here, it's not obvious that it's a happy face. So it took me 1 hour yesterday to actually go through. I downloaded like 380 images for each of those categories, then manually removed all the ones that were not really basically false positives, and I ended up with about 100 faces per condition. So if you go on the maybe you've seen it already. If you go on the GitHub repository, you can download this tiny little dataset that I made yesterday for this lecture today. So I ended up with something that looks, that doesn't look anything because it's, that looks like that. So many different faces, and I've put this small emoji with like disgust, happy, happiness, surprise, sadness, anger, and that's it, and fear there, so that we easily, like, we can spot them easily. And in total, I have something like 560 images, and I made 2 different datasets out of those. One for the training of our classifier with 50 images per emotion, and one for the testing to make to assess whether our classifier is working or not with all the other images. So 258. So we have all those images, but as you can see here, there is a lot of like the pose, the size of, well, the size of the face is always roughly the same, but the pose, the posture is not exactly the same. The background is very different. So using open pose, but actually that's something you could do easily, open face, sorry, but actually that's something you could do easily yourself. We can normalize them, which means doing that. So we remove. So basically, we use. You remember last week I was showing you this landmark extraction thing. So once you extract the landmarks using delib or other libraries, you can easily use the silhouette of the head to create a mask. And then if you have the center of the eyes, it's just a matter of translating, rotating, and scaling a little bit your image to make sure that the eyes of every person on those images is exactly the 2 same pixels in your image, which means that all the image will roughly overlap nicely. So we go from that to that. So for some images it doesn't change much. For some others, like this little girl for instance, we see that the head is rotated and back to the rough same position as the others. And then since I was using OpenFace, I was showing you 5 minutes ago the recognition of action units. There's another little tool that takes a full directory of images and does that, and computes as well all the action units on all those images. So I did exactly that, and I ended up with a big spreadsheet. And for each of the images, I got, so the emotion label is something that I did put myself. I knew, depending on the directory in which I stored the images when I was copying them from Google. And then I have those 17 action units, and as well link to the face. So if you go on the website, you'll see that there is a file called emotion dataset full.csv that contains exactly that. This is that file. And so as I was telling you, there's actually like 3 files, one called full, and one called training, one called testing. And training is a subset of 50 images per emotion. Testing is all the other emotions. So we are all set now to start playing with those information and recognize emotion, build an emotion classifier. The first thing we can play with, yeah, okay, sorry. So that's a summary of what I was telling you right now. So we have 558 faces, between 70 and 130 per emotion, training dataset, testing dataset, and we've extracted the action units. Now, what we want to do again is to train a classifier with our training dataset and then check whether the emotions in the test faces can be properly recognized, so if they match or not their actual emotion. So what are our options there? We already listed them minutes ago. So the first thing we can try, without using the action unit, is just try to do this eigenface approach I was describing a moment ago. So we will take all our faces, project them into a PCA base that should basically like provide us with the main differences between all those faces. And if we have many faces with many different people, and the only significant difference is the expression, we can hope, we don't know if it's going to work or not, but we can hope that it will pick up some of the axes that the PCA will figure out will actually match those emotions. you might already have the feeling that it's not going to work very well, but at least that's something we can easily try and see how it looks like. Once we've done that, we can project our test faces on this eigenface basis, and using KNNs or SVNs, try to match them, classify them as like for their emotions. So it's very similar to what we did before. This face recognition with 6 possible, not people, but 6 possible classes of emotions. Now, we were, as I was telling you, instead of PCA, if we use the LDA, the linear discriminant analysis, we can hope to have much better results. Because in that, we add one more information for our dimensionality reduction tool. We say those pictures are grouped by emotion. So we'll see if first, by using an LDA, we get better results. And that would be using directly the faces, which is nice because it means we don't have to pre-process our image with action units. And when you're doing like some real-time processing of your face on a robot, that's the simpler, the shorter the pipeline, the better it is. But anyway, we can still compare that to the action units we have. And with the action units, the first thing we want to do, so it was, you remember, like we were extracting 17 action units per face. So we can just go for using that vector, KNN or an SVM, and see if we are able or not, just using that with no post-processing on our action unit, able to recognize emotions. If it doesn't work, or if it doesn't work well enough, we can try to first run a PCA on our action units to see basically how our set of action units is organized. And maybe again, if we're lucky, we will see that some action units are actually the one that represent better some of the emotions. And we can try as well with the LDA. Do you have any intuition in terms of how those 3 last ones will comparatively perform? What is your intuition? Beyond the fact that if I put them in that order, it's most likely because I'm assuming it's going to be always like they are going to improve, like each is going to improve upon the previous one, which is not the case actually. Some are better than others and it doesn't match the order there. So actually, let's make it a larger question. What do you think is going to be the best technique here to recognize emotions? And why? Do you have any feeling about it? Go ahead. That's fine if it's wrong. We'll see. When I started that yesterday, I had no clue. I really did not know what would work best. So I had some intuitions. But do you think it's better to start with the faces, for instance, or better to start with the action units? The faces have more information, right? We have all the pixels, so those normalized faces are 100 pixels by 100 pixels, or 12 pixels by 112 pixels. So in total, it's the vector, the feature vector is something like 10,000 something, while the action units are only like 17 degrees of freedom. So it's there's much more information in our faces, right? So the intuition would be, okay, so if we start with more information, there's chances it's going to be harder to classify, but if we can classify it, then it's going to be better because we have more information. On the other hand, action units, we've seen that before, they are not just random features, they do encode as like features of our face that are actually highly relevant to the recognition of faces. So if action units are any meaningful, then they should be helpful to recognize emotions. So hopefully action units should be quite good at that. So my personal intuition when I started was that basically using action units with an LDA would be the best approach. Would work best. Well, let's see. I'm going to show you a lot of Python code. Actually, if you go to the website, the GitHub repository, in the dataset repository, there is a sub-directory called classification, and all those scripts are there. So you can play at home if you want to. You can play at home and try to reproduce those results. You should be able to get exactly the same result as what I'm going to show you today. But I'm still going to briefly explain you how things work. And there's only 2 very simple Python helpers that we're going to reuse later on. The first one is just to read an image. So we give the path to one of those face, and it opens the image using the Python image library. Here, it converts it to grayscale. So im converts L is the code for grayscale, and returns it as a one-dimensional NumPy array. Super simple. So basically, it loads an image, turns it into grayscale, and return a long vector that is all the pixels values one after the other. And the second one is a small function to plot stuff. And I will show you many plots in the coming slides. And basically, the plots we are going to look at are, we've been talking a lot about LDA, PCA. So we have, for instance, our image, which is like high dimensional. We project it into a PCA base, which is much smaller. We'll play with several values, but let's say maybe 20 values, 20 eigenvectors. If we want to visually see how it looks like, maybe you remember the eigenfaces from last week, but it was creepy, fun, but not very easy to compare things with that. What I'm going to do here is I'm going to take one of my test image, project it onto those 20 eigenvectors. And if you remember the principle of the PCA, the eigenvectors are sorted by the first eigenvector is the one that explains the best the variance in the dataset. The second one is the second best at explaining the variance, etc. So the first vectors are the best ones to explain the differences between our faces. So because we are going to display them as we can only display 2D, 2 dimensions on the screen, I'm only going to take my test images, project them onto the PCA base, and show you the first 2 coordinates. So basically, projecting those images onto the first 2 eigenvectors, which are the ones supposed to best describe the differences in our dataset. So this little code using matplotlib, one of the standard plotting library in Python, just do that. It takes as input a list of points with x dimensions, and we'll just plot the first 2 dimensions for all those images points. Okay, so PCA we said. So this code here, which is not very sexy, is the full code that loads the images, project all the training datasets onto a PCA base, and then take all the test images and project them onto the same training PCA base that we've just learned. So even though it's a lot of code, it's actually not a lot of code. Especially because the first, those lines here are just to open the training images. So I open the training.csv file, so with the list of all my training images, and then for each of the entries in this CSV file, I read the image using the helper there. I add the resulting vector in my training images list. I read the categories as well. So I don't know if you remember, but we add their emotions. The number 0 is fear, 1 is happiness, 2 is, I don't remember, surprise, but like there's 6 values, 6 numerical values for each emotion. And face, the column called named face is just a link there. So I read the image using the value of the column face, and then I store for the corresponding image the category, which is actually my emotion, using the raw emotion. So I do that for the training dataset. I do the exact same thing for the testing images using the testing.csv instead of training.csv. And now, because of the magic of Python and SciPy and SciPy, the learn package of SciPy, to generate the PCA base is as simple as creating a PCA object with the number of components we are interested in. So here, for instance, 20. And then I take all my training images, which you remember, it's a list of long vectors of 10,000 pixel values, and I call PCA fit on that. And that generates a PCA basis. And to use my PCA basis, I can call PCA transform, which is really like, if you remember examples from last week, just a dot product between one new vector, which is one of my testing image, for instance, and this PCA base, and I get the output is a new small vector of 20 dimensions here that represent the projection of my image, test image onto this PCA base. And so here I'm plotting two things. I'm going to show you the plot just next. I'm first plotting the training images onto their own training, onto the PCA base that the training images have generated. So because I generate a PCA base with the training images, and my hope is that at least for the training images, it's going to be quite good at separating the different emotions. That would be my hope. And then if it's really working well, if I try the same thing with my testing images, then it should work as well there. But let's see. That's not correct. So we have every single image in my training dataset. So there is in total 300 images, 50 per emotion is there. So if you count how many emojis there is on the screen, there is exactly 300 of them. And as you can maybe recognize them, like the anger, happiness, surprise, sadness, etc., disgust. Well, it doesn't take any superpowers to see that everything is mixed up. Well, there is maybe a small cluster of angry faces there, but it doesn't look good. And if you look at the testing data set, well, there's no chance it's going to be any better if it's already not very good with the training data set. It's not going to be very much better with the testing data set. So now try to think for just a second of your classifier. If we use a KNN, it's really like, so the K nearest neighbor. We have a new testing image, a new face that we want to recognize the emotion. We will project it onto the PCA base. It will end up somewhere there. I don't know, here for instance. There, new face there. The KNN in that case is really like, if I take a KNN with K equal to 1, so the closest neighbor, I don't know, my closest neighbor might be like here, there. We can very visually see how the KNN algorithm classifier will work there. If I take K equal to 10, then it will take the 10 closest faces, emotions there, and the emotion with the most candidates will be the one chosen. We can see there that, okay, if I have an image that end up here, yeah, okay, that's quite clearly, there's a cluster of angry faces there, so it's probably going to be an angry face. But in most of the space, oops, sorry, it's not very easy to see. And our testing images try to map all those testing images onto the training set. We can see that for many of them, our classification is going to be wrong, not to work. Now, I'm going to give you the exact classification results, how good it is. How can we compute that? If we were completely randomly assigning an emotion to a face, what would be the probability of being right?
Uniform.
It would be a uniform distribution, but the probability would be 1 divided by 6. I see the six emotions. If I randomly select one, it's going to be one out of 6. Now, if I want to calculate that, I take all my 258 testing faces. I use my classifier to do a prediction. I check whether the prediction is correct or not. And then I divide the total number of successful prediction by the total number of test images, right? Okay, I think, okay. So, yeah. So that's the result. If you do just that, using like a KNN with K equal to 1, in 30% of the cases, we got it right. So that's not great, because 1 divided by 6 is what average? 17%. 17%. So we are better than chance. It's good, but we are not much better than chance. It means that there is still like 70% of chances that we are going to recognize the wrong emotion in a given image. With slightly more neighbors, it's slightly better, but And an SVM with a radial basis function kernel is doing really poorly. So we are basically a chance here. So that's not correct. But it's fine, it's expected. We are not expecting the PCA to perform super well. What about the LDA, which is hopefully a bit more exciting? So let's try with the LDA. So the magic of SciPy again is that to go from the PCA to the LDA is as easy as importing the function linear discriminant analysis. And before we had PCA equal PCA with the number of components. Now LDA equal linear discriminant analysis with the number of components. And before we had PCA fit, now we have LDA fit and LDA transform instead of PCA transform. It's exactly the same API. And you'll see that in SciPy, they are really good at making sure that all the classifiers are the same API, all the tools to do dimensionality reduction of the same API. So it's super easy to switch from one to the other. The only difference here is that for the PCA, we just call fit and the training images. Here we have to fit training images plus training categories, because that's the whole point of the LDA, right? Is to maximize the difference between classes and minimize the differences within classes. So we do that, we plot our training and testing categories, and we get that. So that's a training dataset. What do you think of that?
It looks better.
It looks more than better, it looks great. I mean, there's a few outliers, which is not surprising, right? My dataset comes from Google, I did some filtering, but I'm sure there's images that are. It looks great. You don't think it looks like suspiciously good? A bit too good. So yesterday morning when I did that, I was like, wow, that's magic, and I was, yeah, but magic doesn't work usually. Magic doesn't exist. So that's interesting. Okay, so anyway, let's assume it's working well. The next step is to project our testing images, and hopefully it's going to be as good as that to classify and cluster our testing images. I'm going to show you the result for the testing images. Oof. Very disappointing. So I was super enthusiastic and then super disappointed. So it seems to be not work at all with the testing data. So when you see that and then that, the first thing you do is you check your code. You're like, oh, I probably wrote something wrong somewhere. But actually, no. What we see here is a typical case of overfitting. I don't know if you've heard about overfitting before, but that's basically when you have a learning algorithm that learns to sort and classify a small data set perfectly well, but is not able at all to generalize to anything else. It's not general enough. It's just you've built something that is specific to your data set. And that happened very easily with LDA, especially because LDA, to work well, LDA requires a number of samples per classes. So here our classes are the emotions, and we have 50 images per emotion, to be much larger than the number of features we have. And here I remind you that the number of features we have is 12,000 features. So we are as far as it gets from the right conditions to use the LDA. We would need to have n roughly greater than 3 times p, the number of features. So we would need something like 30,000 faces per class. That's not going well. It's not impossible, but it would take quite a bit of time with Google to collect that many images. So it's not going to work if we use pixels directly. But you have an idea of how we could work around this issue. What's the problem here? We don't have enough samples to use LDA because LDA requires the number of features to be much smaller than the number of examples. Because it's going to be too painful to collect more examples, more samples, let's keep our 50 samples per classes. Is there a way to make p smaller than?
Don't use the pixels, use the actions.
Yeah, that's what we're going to try before, but there's something simpler than that. Well, there's some
combine them together.
Yeah, but something simpler than that.
Reduce the resolution more.
Yeah, but that's not going to work very well. What did we do with the PCA here? We reduced our images from the 12,000 vectors of 12,000 elements to vectors of 20 elements. The PCA is a dimensionality reduction technique. So if we take our images, we summarize them using PCA or another dimensionality reduction tool to something that is much more manageable for LDA, then we should kind of work around our issue with the LDA. So we can try to do that. Let's try to do that. Reduce dimensionality using PCA, for instance, and then perform an LDA on the lower dimensionality representation. How do you do that? Well, there's nothing magic there. First, you run the PCA, so it's going the PCA is going to run on your 12,000 dimension observations, going to turn them into 20 degrees of freedom. Then we run the LDA, this time on the PCA transform of training images. So this is 12,000 dimensions. This is 20 dimensions. So now LDA is happy. We are roughly in the right range of features with respect to the number of examples we have. And then same thing, we transform our images and we plot them. Let's see. It looks much better. Now we have clearly like a cluster of angry faces there. We have a cluster of happy faces there. We have a bit of a mix-up between surprise and fear, but at least they are kind of separated. And okay, it's still the mess in the middle. So there is still plenty of faces that are not well separated from each other. But at least it's getting much better. We have like a group of disgust faces there. And let's see now, so it seems that our training dataset is doing, of course, it doesn't look as beautiful as our overfit model, but at least it's much better than our PCA attempt, the first one. Now let's look at the training, at the testing dataset. And it's not too bad. Those happy faces here are nicely clustered. Those surprise faces there are not too bad either. Sad faces, so it seems to do something useful. Now if we look at the results, so what do you think? It's much better. It's still not good, but it's exactly 10% better. If this time the SVM is doing much better, and using the RVF kernel, it's 41.9% recognition rate. So we are getting a bit closer to half-half, to 50% chances of getting the right emotion. So, okay. Before playing with the action units, what we're going to do next, let's have a look at this matrix. I don't know if you've seen matrices like that before. It's what we call confusion matrices. Confusion matrix, that's something you will find very, very often in papers presenting results or doing research on classification. Basically, it tells you so that's the true labels. That's the label, the actual labels of the faces, and that in that direction, that's the predicted label. So if we were in the perfect world, if all the faces were correctly classified, then we would have 0 everywhere except on the diagonal, where we would have 50, 50, 50, 50, 50, 50. So 50, all the 50 faces representing the fear emotion would be classified, would be predicted to be fear. All the 50 faces representing happiness would be recognized, predicted to be happiness, etc. So as you can see, and of course if we have only 40% of success rate, we don't get those 50 there. But there is a lot of things that are interesting to see here. So what is the most striking information there? Happiness. So how do you interpret the fact that happiness is like 39, much better than all the other ones? What does that mean? If you have to discuss the quality or the strengths and weaknesses of our classifier, what does that mean? It means that out of 50 faces that were representing happiness, we were able to actually recognize 39 of them as being happiness. So our classifier is quite good at recognizing happy faces. It's not really surprising, right? Because happy faces are really different from the others. It's like this mouth is very significant, and the cheeks and so on. So it's not surprising. we can see that we are doing really poorly with here. And can you tell me what is the most misrecognized or misrecognized emotion? So for instance, disgust was very often confused, interpreted like the algorithm path was presenting anger. So it seems that anger and disgust are being quite confusing. Happiness, sometimes happiness. So when happiness was misclassified, it was often misclassified for disgust. We can see that sad and disgust, so the actual sad faces are often recognized as being an expression of disgust. So using these confusion matrices, we can easily see where are the strengths and weaknesses of our algorithm. So it seems that definitely like surprise, so that fear is hard to classify. Fear will be typically mixed up. With surprise and sadness, and that actually happiness is quite okay, and disgust is like the face representing disgust are actually often correctly classified as well. Well, it's a bit less than 50% of the time, but it's still better than the others. Okay, now let's look at the action units. So we have our 17 action units. Let's try to just run a KNN and SVM directly on them. And actually, I'm spoiling the results here because I've displayed them already. Using either KNNs or SVM, we get above 50%. So let's first have a quick look at the code. It's again super simple. This time to open my CSV file, I'm using directly one of the NumPy function called gen from text, training.csv. If you remember my big file, I don't need the face, the last column. I only need the emotions that I store in training categories and the actual action units. I'm going to store there in training. So using the NumPy, the weird NumPy syntax to extract parts of the table, the array, I can select that. I do the same for the testing. And then, if you remember the code we wrote last week and 2 weeks ago for the, well, 3 weeks ago for the KNN and SVM, it's super simple. If we have imported neighbors and SVM, we can create a k nearest neighbor classifier with k, the number of neighbors being 1, 2, 4, 6, 9. We fit the training data with the training categories, and then we run prediction like that. Predict. Same thing for the SVM. So yes, the first result is it's doing much better than working directly with images. So yes, it does require pre-processing. We need to have all the action units already extracted. But once we have that, it's quite good at recognizing, well, quite good. It's still like roughly one chance out of 2 to get the right emotion, but it's still much better than the other ones. Now, let's have a look at the PCA. If I take all those action units, run a PCA on them, and plot where, so basically in this set of action units, what are the main directions of variance within the action units. What we can see is that, well, actually, yeah, it seems to be useful to actually see that to cluster our emotions. Happy faces are there, disgust faces are there, fear is there. Well, there's still a bit of mess in the middle, but it seems to be useful. If I project on the same basis the testing, my testing dataset, then of course it's a bit more messy because that's images that the PCA did not see before, but still we seem to be able to isolate, create some cluster there, so it seems that it could possibly help. Now if I run again like KNNs and SVMs on that pre-processed dataset, dataset projected on the PCA basis, we see that it doesn't really improve. Actually, the classifiers, the KNN and the SVM, were already quite good and actually better, slightly better at classifying from the direct action units. What about using an LDA? So this time, you remember the LDA to work, we need to have the number of features need to be much smaller than the number of samples per class. Here we have 17 features, 50 samples per class, so we are good. So we can use the LDA, and we see that there is no obvious overfitting. So there's still a lot of mess there, and some nicely separated groups of fearsome faces, surprise, happy, etc. And if we project the test data sets, there is something that is obvious there, is that the happy faces are very easy to recognize. They're all out of the rest of the bunch. And if we look at the results, we can see that 53.1%, that's our best score so far. It's not a big improvement upon what we are using directly the action units, but it's not too bad. Interestingly here, I'm only using the first 5 components to classify. If I'm only using the first 2 components, which means really that using those 2 components, we can see that using this distribution, we are able to reach, like using even like an SVM, an even better score, or at least a something very similar. So that's quite impressive if you think of it, because it means that out of our faces, those random images at the beginning that we've normalized to 100 pixels by 100 pixels, so 12,000 dimensions. We've been able to reduce those 12,000 dimensions to 2 values that allow us to classify, recognize emotions, not in a super confident way, but recognize 6 emotions out of those images. So that's quite cool. It means that so it's using action units underneath, so there's several steps there. But it means that using a carefully chosen set of mix of action units, we are able to distinguish between those 6 emotions quite well. If we look at the confusion matrix, here yeah, so sorry, that's why I was confused. It's not the number of correctly classified faces would not be possible. There's only 70. It's the percentage of correct classification. So that's the reason why I was right. So there is 57% of the happiness faces that were correctly classified in this case. And so using the action units, we see that sadness is better classified than it was before. Fear is not working well. It's very hard. And fear is usually confused for sadness, which is, yeah, I don't know, it's surprising. If we compare the two, yeah, I mean, generally speaking, the action-based classifier works better. We already know that, but they have different strengths. Like for instance, using directly the images, the faces, we were a bit better at recognizing disgust. So we have trade-offs. All right. Do you have any ideas to where we're going to call it a day here? We've been able to develop from scratch a motion classifier building our own dataset from Google, pre-processing the dataset, and testing a range of different combinations of dimensionality reduction and classification. The results are not great. I mean, I'm sure we can do better than 54% of chances of developing it, but it's for a short go at it, it's not too bad. What are your ideas to make it better or to improve it further?
You can tweak which action sets you're using to see if you get better results.
So this kind of manual tuning of the action units would be more. You can do that, but you would hope that your classifier is just going, or well, not even your classifier, but your PCA, for instance, is going to ignore, basically ignore completely the action units that do not help in distinguishing them. So you don't need to do that by hand.
If you've only chosen 17, you might have missed 1 or 2 that were really important.
I'm just going to show you one thing. Might actually fit the distribution. Okay, if you go to the emotions.
I'm not saying increase it, I'm saying trade out some of the ones that might not be so useful. The ones that won't be. I don't know what ones to trade on, so it's when you fix them.
Okay, so if you go to data classification, and you run here, three AINTs. So that's the script that did generate all the plots I was showing you before. What I wanted to show you there is that. Okay. So it's basically when I run the PCA on my dataset, I have a new PCA base. And if now I back project, so I take, I create a new fake image that would be 1 on the first core, like first component of my PCA basis, and 0 everywhere else. It allows me to know exactly what that first eigenvector, how that first eigenvector matches or corresponds to the various action units. So I take just 1, 0, 0, 0, 0, 0 with 20 zeros because I have 20 dimensions, and I send it back to my action units. So it basically tells me for the first eigenvector what are the most important action units. And so what we see is that the first eigenvector is made a lot of the action unit 1, 1.4, a lot of action unit 5, and that's basically it. Like action unit 25 is actually quite important as well, 0.81. But that's really it. Action unit 2 as well. Now if you look at the second eigenvector, so the second direction in my dataset that explains the best the differences between all my points, we see that it still uses quite a lot of action unit 1, action unit 5, and then it adds as well action unit 7, 10, and 25, more than was the case for the eigenvector 1. So to answer your question, we can almost see from that projection. Well, I'm only looking at the first 2 eigenvectors. We should look at more of them, but that some of those action units are completely useless to distinguish between our faces, and we could completely ignore them. Like I don't know which one is the least useful, but like for instance, action unit 45, no one uses it. Well, that's the blink one, so I think it's a bit of a different one. But action unit 23, which is I think, or something like that. I don't remember.
Yeah, so the idea being get rid of 45 and put in number 8.
Yeah, no, of course you could do that, but the thing is, OpenFace is trying to recognize those 17 action units. So I'm using all.
Oh, it's using everything.
Yeah, I'm using all of whatever OpenFace gives me. Of course, you're right. If we had a classifier, well, some tool to recognize all the action units, but in that case, I would just use a vector of 70 features and period. I mean, I'm sure there's also tools that are able to recognize more of those action units, but as far as I know, OpenFace is today the best.
I thought you'd chosen those ones.
No. That's everything that OpenFace can recognize. When I was doing the small demo with my head and the webcam, what you were seeing there was the whole set of action units that OpenFace could recognize, and that's all of them are there. One thing that is quite interesting to observe there as well is for each of my 6 emotions, I have my dataset, right? And I've computed the average of each action unit for each of those emotions to have a rough idea of what, for each of emotions, what was the most important action unit. And what we see is that, I don't know, if we take happiness, for instance, we see like some action units are less important than others. Like definitely like action unit 6, 7, 10, 12, 14, and 25 seems to be really much higher for happiness than they are for fear, for instance. And fear action unit 1 is much higher than happiness there. So we already see, just looking at that some action units are definitely more useful than others for some emotions. Okay, so any other ideas to improve our classifier? What could we try to improve? Well, one thing we can always do is to get more faces. Like we've seen for the LDA, for instance, we did not have enough faces to run it over the faces directly. If we have more faces, more examples, then we might be able to do better. We also want a better dataset in the sense of, maybe that's something I should have asked you before. What is really wrong with the images I collected for this dataset? When you're surprised, are you really like that? No. When you're angry, are you like? Not really. Real world emotions are very, very far from the kind of emotions you like the prototypical emotion that people will enact when you ask them to act as if they were surprised, etc. And there exists there is a couple of datasets that are focusing on making sure that they are using natural faces and natural emotions. But especially when you ask Google to show happy faces or angry faces, you get angry faces that are not natural ones. Which means that I did not plug all the things to try in live whether this classifier we've been working on together would work with my face. It would possibly work if I were like that and with very exaggerated emotions, but it wouldn't work very well on real world expressions. There's one source of feature that we've not used, something midway between using the raw images, the raw pixels, and using the action units. It's using all the facial features that we can extract, if you remember what we've seen last week. So if we were using all those points directly, that might actually be super effective to recognize emotions. It's a bit lower level than action units, but it's not as big a feature vector as using the raw data. And then different classifiers. We are still just using KNNs and SVMs that are really good and sometimes do perfectly well the job, but there is many other classifiers, and we can think of using a neural network there that would, if you have enough layers, that would learn much more complicated ways of separating our clusters than what we can do with an SVM or with a KNN. So that's things we could explore. And just to finish on that part of the lecture, can you tell the emotion out of this face?
It's shocked and disgusted by something.
Maybe it's shocked. Maybe it's happy. Maybe it's sad. It's impossible to say. But the interesting thing, what I like on that picture is the face is very expressive. There is a lot of signals there.